a while ago. So we're going to start off with population growth models. Remember, I'm going to go through and show you and graph this in a little bit, like I say, when we get our friends in here. So I'm just going to go through and talk about it now. But exponential growth. So this is growth without bounds. So basically, if you've got unlimited resources available and space and things that you need, then populations can grow and reproduce. Just continually like shoot up. Now, what are the limits to exponential growth? Food, space, resources, right? So you've got to have resources for individuals. Some people say space is a big one. I mean, some things that's more impactful than others. I mean, if you look at people, space isn't really an issue like in cities because we keep just piling people on top of one another in buildings as you go up and up, right? But in terms of resources that supply those people, that's the big limiting factor. If you look at poorer countries where there's starving babies in Africa you see on TV, that's primarily, those kids are starving because of lack of resources, primarily food. So you have people who are still kind of in this agricultural stage. They're having to grow their own food, and there's very limited food available, and there's not a lot of medicine available. So you have people having lots of babies. There's not a lot of birth control, and a lot of times there's just not, especially in times of drought or famine, there's not a lot of food available. And so you have a lot of kids who are starving. And if we had time, I showed this really good video on apes called Plumpy Nut, and it talks about like there are some solutions to feeding and helping those kids, but it does require a lot of input from richer countries. So anyway, let's move on. So that kind of gives you this characteristic J curve, the exponential growth, and you can see this on page, turn to 1192. So in 1192, exponential growth is kind of that blue line that's going up, the typical J curve that you see. Okay, like I said, we're going to graph these and add them in a little bit. Don't worry about the math on here right now. And then this more S-shaped curve, the red one, this is more realistic type of growth. And this type of growth is called logistic growth, where you have a population that grows, resources they're obviously limited in nature. There's only so many, if you're a squirrel, there's only so many nuts in the forest, right? And so eventually when you start to run low on those, the population is going to start to level out because there's only so much food to go around. Some individuals, you can't just have as many individuals as you want to. So that typical kind of S shape there is called the logistic growth, where you have exponential growth until it reaches K. K we call what? Carrying capacity. Carrying capacity is defined as the maximum amount of individuals and environment can support. So it's either distinguished by K or sometimes it's written out as carrying capacity, but that's what K is. So you have this line that the number of individuals and environment can support. Now, Matthew, can K fluctuate? Yes. Why? What would cause K to fluctuate? Now, let's say we talk about squirrels in the forest behind the school. What would cause the carrying capacity of those squirrels to vary? Yeah.
Forest burned down?
If the forest burned down, that would affect it. That's a little extreme. Okay, yes, that is true. What else?
Nuclear bomb.
Oh, God. Let's think of something more reasonable that might happen year to year.
Drought, snow.
All right, how would drought affect the carrying capacity, Sarah?
It'd be lower.
Why? Drought would affect the number of?
Water.
Thank you, Matthew. Yes, it would affect the amount of water. Good. What else? Well, I mean, if you're thinking about like plants, like oak trees produce acorns. And if you don't have much water, then it's not going to produce as much, right? If you don't have as many acorns, then you're not going to be able to support as many squirrels. So in years where you have lots of rain, then you might increase that carrying capacity if you had more. So carrying capacity can definitely fluctuate. Now, humans can impact carrying capacity by doing what? As the human population grows, where's my drink? There it is. What do you think happens to carrying capacity? Goes up or down? It could vary. Okay, what would cause it to go down?
Like destruction of forests and habitats.
So as humans destroy habitat, like forests and farms, then you're not going to be able to produce as much stuff that humans need, right? So carrying capacity would decrease. Now, we have managed over the last 50 to 70 years to increase the capacity of what, though? Even though we're losing farmland and forest land. The food production has went up. Why?
Because it's more like monopolized and it's industrialized at this point.
It's more industrialized, there's better technology, and there's better techniques. That whole process or arena is called the Green Revolution. Y'all may remember that. But the fertilizers, pesticides, the industry that's going into that's increased the productivity. That has increased the carrying capacity in terms of just food production. Now, that's isolated a lot of times to richer countries. Hopefully, some of these poor countries where you see like starving babies will catch on, and they will have access to some of these better techniques and better production, so we can kind of eliminate that. Now, we talk about this a lot in apes. In order to reduce the number of babies that people are having, what has to go down first? The birth rate or the death rate?
Death rate.
Why do you have to lower the death rate first to get the birth rate down? Like, so let's say in a poor sub-Saharan African country, women are having on average 6 or 7 babies per woman. Why would you have to lower the death rate in order to lower their birth rate?
Because they're having like 6 or 7 babies, and like 2 or 3 of them are dying.
Okay.
More of the babies will survive.
Well, I mean, but if more babies survive, why are they going to have less babies then?
Less
It's like
mouths
they
to
can't
feed.
provide for any more. It's like
Maybe they can't provide for any more. Typically what happens is you need to lower the death rate first. And so once you lower the death rate, and then there's more medicine in play, which usually helps with the death rate, then women get on birth control, they can family plan, they can get a better education, their kids can get a better education. Just think about it in terms of resources. Like Sarah, let's say you were going to have, you were going to teach and make $50,000 a year, and you had X amount of money that you could spend on your kids to send them to piano and soccer and stuff like that. Well, let's say you wound up having 6 kids. What's that going to do to your kids' ability to learn and do stuff and be productive? Decrease it, because you're going to have to spread that out amongst all of them. Whereas if you only have a couple, 1 or 2, then you could spend more money on each individual kid and then invest in them. And typically that's what happens as countries become more and more developed. People have less kids, and kids are more expensive because those countries are getting more developed. Things cost more to invest in them. But and because they cost more, people tend to have less and less offspring. And they often want to have more time for themselves and do more things for themselves. A lot of times in poor countries, people have lots of babies, not only because they don't have birth control and some of the issues related to that. Oftentimes they have lots of babies to help do what?
Help like work out.
Yeah, help work around the farm and stuff. Like if you look at America 100 years ago, you would have seen, like my grandmother had, I think, 10 people in her family, 10 kids. And that was pretty common around that, time, because you had a lot of people who lived in rural areas that needed lots of kids to farm. And the girls helped take care of the kids that were growing up, the older ones, and so they kind of helped raise them. And then the boys a lot of times worked around the farm. And so there's a reason you see the growth that we had. All right, but eventually as countries become more developed, those numbers go down because it becomes more and more expensive to have kids. Okay, carrying capacity. Let's look at ZPG. If you go back up to under Part A, number 6. Zero population growth. Where does that occur on this curve on 1193?
At the carrying capacity.
At the carrying capacity, where the line's going straight across. If the line's going up, what's happening to growth? It gets positive. It's going up. If the line's going down, it is negative. So if the line's going straight across, that means you've got ZPG. You've got zero population growth. It's staying the same. Now, in order for a population to stay the same, how many babies does the average woman have to have?
2.
Theoretically 2, but not exactly. You've really got to have about 2.2 on average. Why? Y'all should remember this. So you got to have, if you're a couple, you got to have 2 kids to replace you, right? Why would you need to average a little bit more than 2 though to replace you? What?
Like this.
Yeah, I mean, some of the kids aren't going to make it to reproductive age. Maybe something happens to some of them. Some of them aren't going to be able to reproduce just naturally. So you've got to have a little bit more on average to reach that reproductive level. The Earth is getting to where, or the human population is getting to where that reproductive replacement level is getting closer to that like 2.2 number. So where the population should start to level off. Now, if we hit 2.2 on average, does that mean the population is going to stop growing? No, not for a while, because you've got another issue because you've got people who are living longer. So even if people stop having more babies, a lot of the babies that are being born now are going to live much longer than the people that are around now. So you're going to have babies that are going to live longer, and they're going to fill in these older age groups where they haven't historically done so before. So the human population on Earth, if you look on page 201, this book, I mean, I feel like I just got this book new. The human population's at 7 billion. We're almost at 8 billion now, right? So, and you see it going up exponentially there. Now, that population's going up, and it's going to continue to rise and probably get to about 10 or 11 billion by 2050. We're almost at 8 now. And what was this? In 2012, we were at 7. So that means in about 9 or 10 years, we grew a whole billion. So we better hope we start leveling off if we want to the human population is expected to level out about 10 or 11 billion by 2050, maybe a little bit after that. What area on Earth is going to experience the most growth from in the middle to latter part of this century? What area is still going to be growing? Yeah, sub-Saharan Africa. So this is going to go into, and we'll talk more about this in apes, but basically as countries become more developed, people have less kids. And so that's kind of the last place where you have people where it's less developed, people are still having lots of babies. And so in order to get the lower number of kids, you have to develop those areas. And that's probably going to be the last area to kind of really develop and get that number down. All right, what else did we miss? Zero population growth. Pioneer species is one I forgot to mention. When you talk about starting out in an area, those are the organisms that first start to move and grow in an area, and they're the ones that typically grow the fastest. You see this rapid growth. But as succession takes place over time, that kind of levels out. So we'll get into succession later, and I'll come back and talk about pioneer species. And then lag time, or an overshoot. Now, your book doesn't really show this. I'm going to graph it out for you here in a second, where most of the time a population, like on 1192, doesn't just get to, actually look at 1193 at the bottom. Y'all see the Daphnia on the right side on part B? What happens to their levels as they get close to like 60 to 80 days? Does it just level off?
No, that's fine.
It spikes. You can see a spike down here. It goes up and then it settles back down around carrying capacity. So this area where it's up, I wish they'd drawn this with a line, that's the overshoot. Think about it in terms of squirrels. Let's say you're squirrels and you've only got so much food available. What's that movie, Over the Hedge? And like there's only so much food available and it's wintertime and it's mating season and you're like, you know what? You and your squirrel friend, you're sitting around and you're like, I just don't think there's going to be that much food next year. Maybe we need to hold off on reproduction this year. Yeah, let's do that. Let's just enjoy our time out here in the woods. Do you think that ever happens, Matthew? With squirrels? You think they're discussing if they're going to reproduce or not? Or do you think the rhythms of life are compelling them to do their squirrely things? Yes. And so they're not really thinking or planning out like, hey, we might have some babies that might not make it because there's not enough food next year. They're thinking about reproducing. So oftentimes what happens is you have the population will go more than it can hold, and then it kind of levels back out when some of those individuals die off. So that is the overshoot. All right, the allele effect, the last one on there. Read that for us, Walker.
Where's this?
Last part of part 2 notes.
I don't think I have the back of part.
Is that on y'all's?
Yeah.
Mason, read that for us.
This situation occurs when you have a small number of organisms. This low number causes inbreeding to occur, and then this results in no variation for a gene pool.
Okay, stop there. All right, so basically what the allele effect is, when a population gets so low that it decreases to a point where there's just not enough genetic diversity for individuals to survive. There's too much inbreeding going on. Y'all may have heard of the northern, I think it was the northern black rhino. There was a subspecies of rhino, and there were like 4 females left, and there was 1 male, and they tried to get him to mate with the females, but he couldn't do his thing, and then so they wound up, he died, and then so basically there's going to be no more rhinos. You know what I'm talking about?
Yeah.
I heard of this? So essentially, that's what we're dealing with, where you wind up with so few individuals that there's just not enough genetic diversity to continue. Okay? All right, so let's go back and look at 1193 real quick, and let's draw this out, see what it looks like. So exponential growth, we start out, what does it look like? What's the shape? Okay, so we've got this, remember on the x-axis, what do we have? Okay, so we got time. Now, sometimes as a function of time, you'll see generations. So they'll have like so many generations of individuals, but if you see that's just a function of time. And over here on the y-axis, what do we have? So the population size. Okay, so we start out low. We have this typical kind of J curve where we have exponential growth. Okay. Now, once we reach a certain point, what happens? Why does it start to level out?
Because there's a carrying.
They run out of resources.
Do what?
The species run out of resources.
Yeah, so we start to run out of resources, and because of that, the numbers will start to level out. And so typically what happens is we have a little bit of overshoot, and that line right there represents what?
Carrying capacity.
Okay, so carrying capacity, where there's only so much food, resources available for individuals in that area. And so the overshoot, like we said, is where they just had too many babies. There's not enough resources, and so some of them are going to die. Okay? And what type of growth takes place right here as it levels out? What is it called? ZPG, zero population growth. Good. All right, and this kind of overarching shape here, loosely kind of looks like an S, is called what? What? Logistic growth, yeah. So this is your logistic growth curve, this S shape. Okay? All right, so let's talk about population growth a little bit. There's some math we need to do, and y'all need a calculator for this, but y'all keep out your notes. And if you look over on part 3 here, it talks about limiting factors. But let's look at some different aspects of population growth. So if you guys are asked to calculate this, what are some factors that go into populations growing or declining? Okay, birth rate does what? Increases. What else increases? Immigration. So birth and immigration are going to be positives. And then what's going to cause a decrease? Death and immigration. So with the E, yeah, so both of those are going to cause decreases. So let's say you have, so some of you apes people are going to know this. Normally when you look at census or population data, they give it in per 1,000 individuals in a country. And so let's say we have our births, our deaths, our immigrants, and our immigrants. Okay, so these are normally given per every 1,000 people. Let's say there's 42 births, 17 deaths, 13 immigrants, and 3 immigrants. So what I want you to do is to see if you can figure out how to calculate how much that population will grow. So for every 1,000 individuals, this is how many births there are, how many deaths there are, how many immigrants there are, and how many immigrants. Okay? So you need to put those together and see if you can figure out like what's going to happen to that population. Let's say this is happening over the course of a year. So essentially what you're doing is calculating the percent change in the population. Okay? So I know some of y'all hadn't done this before. It's okay, just try it and then we'll work through it, okay? that number from? What about this number? You're not dividing, you're subtracting. Yeah. You know what to do?
I already did it, I'm just redoing it again, just check.
What do you got? You have any idea what to do? What you? Sure.
Yeah.
Alright, first thing, easiest thing to do here is figure out what we're adding and subtracting. First, they're gonna be a what?
Positive.
Positive. Okay, so we're gonna add that. Deaths are gonna be negative. Immigrants are gonna be?
Positive.
Immigrants are gonna be?
Negative.
So, all you gotta do is add those up. Okay? So add those up. Did you get this, Mason?
Yeah.
All right, Sarah, what you got?
35.
Okay, so we've got 35. You got a plus 35, right? So for every 1,000 people in the population, we expect it would go up 35. Okay, so 35 increase for every 1,000 people. And to find the percent change, what do we need to multiply that by? 100. Okay, and so you just cancel out your zeros, divide 35 by 10, and so our percent growth rate would be what? 3.5. Okay. Any questions on that one? Now, another thing you can do, I talked to Ms. Mara about this the other day, we can take this number and we can use it to figure out how long it would take this population to grow and double. Okay? So, you remember doubling time? So, doubling time is how long it takes the population to double. So, if it continues at the same growth rate. The same applies, you can do this for calculating your interest or if you have stuff in the stock market. It's just a quick and easy way to figure out how these numbers are compounded. Okay? So if I were to, let's say I ask you, just do this off the cuff, and none of you H people answer this. Let's say that I ask you if you've got a population that's growing at 10% a year, how long would it take that population to double? 10 years, right? So it'd be at 100%, that would double. That's wrong. Okay. So, because each year, like if you had like 100 people and it grew 10%, well, after the first year, it would be at 110, right? But if it grew at 10% the next year, it would be growing like 11, right? So it increases the amount every year. So you've got to figure that increased amount in, okay? So, in order to do that, there's a simple way. All you do is take your percent growth rate, take 70 and divide it by your percent growth rate, and that'll give you your doubling time. Okay, so calculate that real quick. Because that's what the internet says, and it works out. Some places say 70, some say 72, I don't know. Some mathematician figured this out. Kudos to them. Okay, so what'd you get, Mason?
20.
Okay, so if that population in that country is growing at 3.5% yearly, you take 70 divided by that, and it should take 20 years. In 20 years, that population, you would expect it to double. Okay? Does that make sense? Now, we'll take this another way. Matthew, let's say that you invest in some stocks, and you get a 7% return every year on your stocks. Kudos to you. Okay, how long is it going to take your stocks to double?
7 years.
You're getting 7% increase.
10 years.
10 years. So at that 7% increase, it'll take you 10 years for your money to double. Remember that. Okay? So it's just a handy way of remembering how quickly it can double. All right. One other thing we need to talk about on part 2, and then we'll weigh our plants here in a second. Age structure diagrams. So age structure diagrams. I'll tell you what, I don't even care about the book. Let's just look at these on the board. Age structure diagrams, or they call them age structure pyramids in your notes there. These are diagrams that show how populations are growing or changing. Okay? So we're going to look at 4 main types of these. Like I say, most of you people in apes have seen these before. And I'm going to draw them out, and I'm not a very good drawer, but y'all get the idea here. So we've got one pyramid, we've got another one. It's going to look kind of like this. The pyramid's a little crooked, like my head. And then we've got one that goes pretty much up and down. And then we got one that kind of goes up like this. Okay? So, when you're looking at age structure diagrams, there's 3. The easiest way to do this is to break it into 3 different parts. Okay? What are they, Nathan? You remember? No? Miranda?
Like birth rate and death rate and all that.
Okay, well, sort of. Okay, we're going to divide it into 3 parts. From about 0 to 14 years, and then we're going to go about 46 to whenever, and then this one is going to be about 15 to 45. What happens at 15 to 45? Reproductive years. So you've got pre-reproductive years, you've got reproductive years, and then you got post-reproductive years. Why is it important to look at it in those 3 categories? Yeah, to see how it's going to grow. So we know who's having babies, we know who's fixing to have babies, and we know who's not going to be having any more babies. Okay? So that's generally the way you're going to look at these. So we just kind of divide them all into the 3 categories. And so let's describe their growth. So if you have a country that has a pyramid like this, where they have a lot more young people than they do old people, what type of growth would you expect would happen?
Exponential.
It's going to grow pretty fast. Why?
Because you have so many, people that are reproducing now and they're about to reproduce.
Yeah, so you've got a bunch of people now. Just think about how many are reproducing, and it made the curve that big. If all of these individuals in 14 years are up here, then they're going to be having lots more babies. So you would expect rapid growth to take place here, okay? Okay, and we see some of this in usually our poorer, more developing countries where you have lots of babies and not as many are dying. So you may have places where there's 4 or 5 babies being born per woman, and then they may lose 1 or 2, but they're still much above replacement level. Okay, this one, do we have any growth happening here?
Yes.
Yes, but it will be what type of growth?
Slow.
Okay, so this is your slow growth. This is typically in your transitional countries where they're transitioning, they're getting more and more developed, but the replacement level is still a little bit above 2.2, okay? So the U.S. also kind of falls in this slow growth pyramid, although it doesn't exactly look the same. You might see a little hump up here at the top. I don't know, I'll draw some ears on that. Why would the U.S. have some slow growth occurring?
Immigration.
Yeah, immigration. So we have a steady stream of immigration, so there's growth taking place there. And then this one, what does it look like?
0% growth.
Yeah, so this is your ZPG. This is where countries level out. A lot of Western European countries, some of your other developed countries where they're pretty much at replacement level, or they're maybe a little bit below replacement level and they have some immigration, their population's not growing, so it's pretty steady. And then the last one over here, what do we have?
Declining population.
Yeah, we've got declining. So declining happens when your country gets what? Old. So you've got a much older population than you do a younger population. Now in your notes, Walker, what do we know about China and their population, how many babies they get to have? Well, just in general. You know? How many babies can you have if you're in China? 2? How many babies could you have in China back in the day?
Is it 1?
Yeah, China was notorious for a long time for their one-child policy. Why did they put that into play?
Because they had a rapidly growing population.
Yeah, they had a very rapidly growing population. That's why their population is about 1.4 billion right now. So they put a policy in place and said, we're not going to let people have as many kids. You can only have 1 kid unless you're like a poor farmer out in the middle of nowhere, okay? Now, they relaxed this, I think it was 2 years ago, back to 2 kids. Why? What do they find happen from this long one-child policy?
Their population's getting older and they don't have many people in the workforce
That's right. So once you get here where you have a lot of older folks who are retiring and you don't have many people down here, then how are you going to replace all those individuals that are supposed to be working and doing things that's needed to keep the economy up? So, and you see countries like probably the worst one is Japan, where replacement levels, how many babies do we have to have, Mariah, in order to keep the population stable? 2 or about 2.2. Japan's at roughly like 1.3 to 1.5. So what does that mean for their population? They're declining rapidly. So they're giving like massive incentives to try to get people to have babies so that they maintain that. That's huge older population, and there's not a lot of younger people to help take care of them or do the work as those people retire. Okay? So that's an issue. What else did I have on here? Oh yeah, we talked about doubling time, survivorship curves. So this is kind of the transition as countries become more and more developed over time. Okay? All right, so let's take a few minutes now in our population growth. So for our observers in here, how did the human population transition from hunting and gathering to farming? So what's the benefits of farming?
You can stay in one location. You can grow your
Control.
You can stay in one location. You can what?
Control the food rates.
You can have a better control of the production of food. And what's the other benefit to staying in one location where other people are?
You can make a big community.
You can make communities, towns, and because of that, you have more what?
advancements and like technology.
Well, you do have more advancement. People can specialize in stuff, and you also have more safety, right? So there's safety in numbers, assuming you're all getting along, fairly with one another, which is different than if you're in small tribes and you're moving around from location to location looking for food. You may come onto another tribe's land. Y'all may get into it. Somebody may get knocked in the head. Who knows what happens? So that's the benefit of moving to this agricultural type of lifestyle that you see. Then there's movement from that. We see in the late 1600s, 1700s, probably more 1700s, to this industrial revolution where you start having machines, better tools, the discovery of fossil fuels where you have energy sources that you didn't have previously. And so you have more energy, you can make more food, you can make more stuff, and the population shoots up significantly, right? So that was the contribution of the Industrial Revolution. And we still see that kind of, there's lag time. If you think about the U.S. and then think about where India is kind of like at the beginning or kind of earlier part of the Industrial Revolution there, where people are getting more machines, they're using more tractors and stuff for farming, stuff we were doing 70, 80, 100 years ago, right? So there's a lag time for different countries. Now we see this movement into the technological revolution. And what does that mean for us in terms of growth?
Better healthcare.
Okay, better healthcare, better medicine. What else? What does it mean for birth rate? What do you think?
Decrease.
It's going to increase?
It's going to decrease.
Decrease. Why?
There's more survival rate.
Well, there's a higher survival rate. People don't have to have as many kids. And also, it's more expensive to have kids. And you've also got better medicine and technology. I don't know if y'all remember that video from Bangladesh we watched. Bangladesh is one of the most densely populated countries in the world. And so they've made this push to give people birth control and talk about family planning so that they won't have so many kids because the population is so dense and it makes it difficult on the society. So you see more of that with the technological revolution. A lot of times, like in Japan, you see that kind of like going so far as the population starts declining. People want
What
to...
happens in those countries in the next 34 years?
I think the population declines significantly. I think Japan is very anti-immigration. They really like a cohesive culture. They want to maintain that. And not that there's anything wrong with that, but because of that, you don't have many immigrants coming in, and if you're not having many babies, then you're not going to be able to increase the population. So the projections are countries like Japan and a lot of Western European countries, the population will decline over the next 50 to 70 years. And some of these other countries are going to continue to grow and increase.
So you don't think there will be any rebound in birth rates?
I don't think there's going to be a lot of rebounds there. They're trying to heavily incentivize it monetarily, and I think people are just like, I'd rather spend my money on me. I'd rather wait later to have babies, and because of that, it's hard to get people to have kids. Kids are a lot of work and a lot of trouble. I love my kids, but You know, and they're expensive. So
Do you think
we'll see how that.
they're gonna change immigration policies and there's gonna be rapid immigration into this country?
I do think you're going to see movement more than you have in the past of immigrants. Yeah. So we'll see how that affects populations as well. All right, you guys take care.